We're now going to take a look at how to apply the Java CountDownLatch in practice. And this particular example comes from a really cool program that I have in my GitHub repository that does some interesting things. And I'll actually run the program for you here once we have a chance to kind of see what it's doing. So this is another variant of the greatest common divisor application. And what this does is it's going to use a couple of CountDownLatch objects to coordinate the concurrent benchmarking of 4 different algorithms to compute the greatest common divisor. So if you take a look at the link at the bottom of the slide down here, you can actually play around with this program, and it basically looks like what we're seeing here. Again, hopefully without being too verbose, GCD is just something that computes the largest positive integer that's an even divisor of 2 numbers. So the GCD of 8 and 12 is 4. So you probably knew that already, but just to reinforce that. This particular program tests 4 different ways of computing GCD. Uses the GCD method defined by the big integer class, which allows for arbitrary precision GCD. As we'll see when we look at the performance, this version is rather slow, but the benefit it has is you can do arbitrarily large numbers and compute their GCD. There's also an iterative version of Euclid's algorithm, which is kind of the classic way of doing a GCD. There's also a recursive version of Euclid's algorithm, which is perhaps arguably simpler to understand, although it's recursive, so it's a little bit slower. And then finally, there's the most complicated version in terms of its implementation details that uses binary arithmetic. I won't really spend a lot of time on how this works, but if you're curious, you can take a look at the link at the bottom of the slide, which shows you how you can use bitwise operations to do a binary version of the GCD algorithm. As it turns out, that's probably a win if you're programming assembly code, but it's not really a win here. For the particular details of our example, the implementation of the algorithms don't really matter. It's not important, but it is important that we have 4 of them. And we want to be able to benchmark them to see which one or which ones run the fastest. So let's take a quick look at the GCD CountDownLatch test class. We'll walk through the code. So if you take a look at the link at the bottom of the slide, you'll find the source code for this. And what this does is it creates worker threads that use entry and exit barriers to create CountDownLatch objects. So this thing is called GCD CountDownLatch test. And this is the entry point into the test. And we go ahead and make tuples. Each tuple is going to be a different one of these algorithms. Again, recursive Euclid, or the version that's the iterative version of Euclid, or the binary version, or the big integer version, and so on. So we have a list of the algorithms. We then go ahead and create an entry barrier. As you can see, we're going to have it be a CountDownLatch with the count of 1. And then we go ahead and we create an exit barrier, which is going to be the number of tests that we're going to run. So again, we have 4 algorithms, so it's going to be a CountDownLatch with the value 4. So the exit barrier has a count of 4. We then go ahead and we make a new thread that's going to run the CountDownLatch worker class, and it's going to do that for each of the tests that we're running. So for each of the tests, it's going to go ahead and create a new thread, and it's going to start that thread. So you can see here that it's going to start each of these threads. So again, we have 4 algorithms, so we'll have 4 threads. But rather than letting the threads just start to run right away as soon as they're started, which would be unfair because whoever started first would get a head start, instead, we're going to pass in the entry barrier and the exit barrier, and we're going to use the entry barrier to make sure that none of the algorithms start until they're all ready to start. So we print out, we're starting the tests, and then we tell the entry barrier to count down. And so what that does is it basically says the worker thread should all start running. However, the interesting thing about this is using a countdown latch here doesn't ensure all the worker threads start at the same time. And we'll talk about that in more detail when we talk about the cyclic barrier. The cyclic barrier gives us a a little bit more control over how this all is going to work and makes it even more fair. This calling thread, the main thread, if you will, is then going to call the exit barriers await method. And that, of course, is going to block until all 4 of the algorithms all finish their processing. Now, after this await call returns, we can't reuse the countdown latch without making a new one again. So we'd have to write a loop or something if we wanted to go back around and recreate the countdown latch again, because countdown latches are not cyclic. They're only good for one shot. So let's take a quick look at the CountDownLatch worker class. So you can see that the GCD CountDownLatch worker class implements runnable. So that, of course, means it can run in a thread, a background thread. It's got a couple of synchronizers, a countdown latch for the entry barrier and a countdown latch for the exit barrier. And those are initialized with the constructor that we see here, along with some other stuff. And then here's the run hook method. And this is what's going to start after the thread has been started. So we come over here and we say entry barrier await. And what that means is await for the main thread to say all these other threads can start to run. But notice that the way the test is set up, if we look back over here, the countdown call here is done shortly after we've started all the threads. So once countdown started, then the threads can begin as long as the main thread has done the countdown. What we probably should do here to be a little bit more likely to be fair is to put some kind of a timeout, like have that main thread sleep for a second or something, just to let all the other threads be up and ready to go before we do the countdown. But I wanted to demonstrate the downside or the limitation with countdown latch, which you don't have to wait for all the other threads to be in position before they can start to run. So at this point, then the threads can run as soon as the entry barrier has been counted down to 0. Then we go ahead and run the test. Each of the algorithms does their own thing. And then as each algorithm finishes running in its own thread, then it calls the countdown method, which decrements the count and then lets the main thread proceed when the count reaches 0. So we're now ready to go ahead and start running the program. As you can see, we've got 4 different slots here, kind of like racetrack, where we have one for recursive Euclid, one for iterative Euclid, one for the binary GCD, and one for the big integer GCD. We come up here and we click on the button, and we're going to take the default number, which is, as you can see, very large. So let's start things running. And you can see that down here, we're counting down, or actually counting up the time, and recursive Euclid and iterative Euclid and binary all finished pretty quickly. And good old big integer is still cranking away. It's going to take it a while to actually run. And the reason for that is that it's just very inefficient relative to the other implementations. The nice thing about the big integer version of GCD, of course, is that you can do it for arbitrarily large values, whereas for the other ones, we're kind of limited by the precision of, I believe in this case, longs on the machine. So it's cranking away, and I think we can go ahead and stop it by clicking the button again, and you can see it knows how to interrupt. But basically, this is just demonstrating how we can time the different results. So if you want to get more information about how all this works, go ahead and take a look at the code. And it's a nice example of how to show some benchmarking. And since I have a multi-core processor here with, in this case, I think it's 8 cores, then each of those different tests was running on its own core. And that's why they were able to run very quickly.